Hello everyone, welcome to our LeChateliers principle video. So in the previous video we talked about equilibrium. If we leave any reversible reaction sitting long enough, it'll reach this state where the rate in the forward direction matches and cancels the rate in the reverse direction. And a reaction at equilibrium will stay out that way forever or until we change conditions somehow. LeChatelier's principle deals with what happens when we change those conditions. And very simply put, it states whatever we do, the reaction is going to shift to undo. If we add more of something, it's going to use up the excess. If we remove something, it's going to shift to replace the stuff we removed. If we compress it into a smaller volume, it'll get smaller. If we expand it into a bigger volume, it'll expand, and so on and so forth. So let's go through and look at the specific examples now. So starting out with adding more of a chemical. So if we add more of a chemical, let's say more reactant, in this case either hydrogen or iodine, we're going to use up the extra reactant and shift towards the right and make more product. So again, to reestablish balance, we have to use up the excess reactant and form more product. A previous student of mine gave me this fantastic analogy. He said it's like 2 buckets of water connected with a pipe. If we dump more water in our left bucket, it's going to have to flow through the pipe towards the right or towards the product side to reestablish balance. Now if we add more product, more HI, we're going to have to use up the excess HI and shift to produce more hydrogen and iodine. We're going to have to shift towards the left or towards the reactant side. And that would be like if we dumped more water into our right bucket, our product bucket, we'd have to flow towards the left or towards the reactants to reestablish that balance. Let's talk about what happens when we remove something. If we remove either of our reactants, in this case hydrogen or iodine, we're going to shift towards the left to replace that. Going back to our buckets example, imagine we scooped a bunch of water out of our left bucket or our reactant bucket. In order to reestablish balance here, water would have to flow into the left or the reactant bucket to, again, reestablish that equilibrium. And similarly, if we remove product, we're going to have to shift towards the right or towards the product side to replace it. It would again be like scooping water out of this right bucket here. We'd have to shift towards the right or towards the products to replace it. So let's talk about what happens when we change our volume and or our pressure. So this comes into play if we have a differing number of moles of gas on either side of our equation. If we decrease our volume or increase our pressure, in other words, if we compress our reaction, we will always shift to the side with fewer moles of gas. In the example given, that just happens to be the right side. It won't always be the right side, but in this case it is. So again, if we decrease our volume, increase our pressure, compress our reaction, we'll shift to the side with fewer moles of gas, which in this case happens to be the right side. You can see we have 2 moles of gas over here, and on the left side we have a total of 4 moles of gas. Now if we do the opposite, let's say that we increase our volume and or decrease our pressure, we're sort of expanding and giving our reaction more volume to occupy, it's going to shift towards the side with more moles of gas. So it's going to expand to occupy this extra volume that we've given it. Moving on, talking about the effects of temperature, temperature effects depend on whether or not our reaction's exothermic or endothermic. If you've forgotten those terms, endothermic means that heat is a reactant, our reaction absorbs heat, and exothermic means that it's a product and it releases heat. So in the case of endothermic reactions, if we increase our temperature, it's like adding more reactant. We're going to use up the extra reactant by shifting towards the right and making more product. Now if we decrease our temperature, it's like removing a reactant. We're removing heat now, so we're going to shift towards the left to try and increase that amount of heat, replace the amount of heat that's been removed. Now if we talk about an exothermic reaction, heat's now a product. If we increase our temperature, it's like adding more products. We're going to shift towards the left side to use up the excess product that's been added. If we decrease our temperature, it's like removing a product. We'll shift towards the right or towards the product side to replace that heat that we've removed. So this handy table right here sums up the things we've talked about and includes another one that we haven't discussed yet, and that's the effect of a catalyst. We mentioned in a previous video the catalyst speeds up the rate of reaction, but it actually has no effect on our equilibrium. It'll speed up the rate in each direction equally, but we won't shift the equilibrium. It won't affect our ratio of products to reactants because the amount it increases our rate is equal in the forward and reverse directions. So please pause the video and complete questions 1 through 4. Welcome back, everyone. Let's talk about an applied example now. So if you read the introduction in the activity, this reaction is pretty fascinating in my opinion. This reaction really changed the whole course of humanity. And so in this reaction, we are going to take nitrogen and hydrogen and use it to produce ammonia. This reaction is exothermic. And so we talked about LeChatelier's principle. LeChatelier's principle is not only incredibly important in biochemistry, it's also really important in industry. So our reaction works by pumping hydrogen and nitrogen into a compressor and into this reaction chamber where we're going to produce a mixture of nitrogen, hydrogen, and ammonia. So reversible reactions never actually reach completion. We won't actually use up all of our reactants because our ammonia is actually decomposing back into reactants. And so why the compressor? Well, we want to press these together because we see the right side has fewer moles of gas, so the higher the pressure, the more product we're going to produce. Now from there, we're going to pump it into this condenser. And we're actually going to sort of allude to some Chapter 5 stuff here. So when it comes to Chapter 5, we talked about intermolecular forces. Nitrogen is a nonpolar molecule, meaning we have only weak dispersion forces between those molecules. Hydrogen is also a nonpolar molecule, meaning we again have only weak dispersion forces. But ammonia is very polar and it has hydrogen bonds. And so we have strong IMFs, meaning that we can, at relatively high temperature by gas standards, liquefy this thing. And so ammonia's got such strong IMFs that although it's a gas at room temperature, on a cold winter day it's able to liquefy. So we liquefy our ammonia, we remove it from the mixture, so we're removing a product here, we're going to shift towards the right to replace it. And so we just pump our unreacted gases back into our loop and we just keep cycling it around. I think this is really clever. Now, I want to mention that the tricky part here is the temperature. If our reaction's too hot, then we get a poor yield of ammonia because adding more heat is going to shift us back towards the left. However, if our reaction's too cold, then it goes too slowly. So scientists have to play a lot of crazy tricks to get a good yield of ammonia, a good sort of favoring of our right side of the reaction, but at the same time not have our temperature too high so that our reaction goes really slowly. And that's kind of the purpose of the catalyst here. It's another way of speeding up the reaction without requiring a very high temperature. So please pause the video and complete the applied example. Once you've done that, shoot on over to the discussion section and participate with your classmates.